Hi everyone, let's talk about the modular arithmetic contradiction trick for Diophantine equations. So let's take a look at an example because this is best exemplified by a concrete example. So I'll show you what's called the Lewis equation, and this one wants you to find all x and y that are an ordered pair in the integers such that x cubed minus 117y cubed is equal to 5. Okay, so it's not clear how to solve this right off the bat, and people have written several papers about this equation until somebody pointed out a simple trick that could solve it. So I'll show you what the trick is. First of all, notice that 117 can be written as 3 squared times 13. So that means that 9 divides 117. Now it's not clear why we're taking the factor 9 in particular, but that's going to be the most important observation. So modulo 9, this equation becomes x cubed is congruent to 5 mod 9 because the 117y cubed term gets annihilated. Okay, so now what this means is that we're to find x such that its cubic residue of x cubed is 5. So let's take a look at what happens to the various residues from 0 through 8 if we cube them. 0 cubed is congruent to 3 cubed is congruent to 6 cubed, and they're all congruent to 0 modulo 9. We have 1 cubed is congruent to 4 cubed is congruent to 7 cubed is congruent to 1 modulo 9. And we have 2 cubed is congruent to 5 cubed is congruent to 8 cubed, which is congruent to 8, otherwise known as -1 mod 9. So we have 0, 1, and 8, and none of them are 5 modulo 9. That means there are no cubic residues of 5 modulo 9, so this over here is a contradiction. So that means there are no solutions. Now I want to mention a caveat, which is that this is not guaranteed to work. There might be there might be equations that have no solutions, but you can't find a modulus like this, or at least you can't find a convenient modulus like this. And there might be equations that have solutions, and you're looking for a modulus and you won't find a modulus like this because there are solutions, but maybe they're so large that you can't find the right modulus. So there is no specific science behind finding the modulus. It's just you can follow some heuristics, and what I'll do is that I'll give you some heuristics. First of all, choose a modulus that annihilates coefficients. So you want to get rid of coefficients like we got rid of 117. Choose a modulus that is a factor greater than 1 of several coefficients. That way you can annihilate those coefficients. By annihilate, I mean they get sent to 0 modulo your modulus. 2, choose a modulus with very few nth power residues. And that's assuming your equation has x to the power of n. So x to the power of n will have very few residues, which will reduce the chances of that colliding with other terms to produce 0 in the end. Because you essentially have this equation, if you put everything on one side, is congruent to 0 mod your modulus m. And so if your terms have very few power residues, then there's, in some heuristic sense, a lower chance of them combining with addition and multiplication and subtraction to produce 0 in the end. So I'll give you some examples of that so that you know in a concrete sense what I mean. So x squared is congruent to 0, 1, and 4 modulo 8. So how do we find that? We just we consider all the residues modulo 8. So 1 square is, well, 0 square is congruent to 0, 1 square is congruent to 1, 2 square is congruent to 4, 3 square is congruent to 1, 4 square is congruent to 0, 5 square is congruent to 1, 6 square is congruent to 4, and 7 square is congruent to 1. So we have 0, 1, 4, 1, 0, 1, 4, 1. So, right. And similarly, so that's one example, A. We also have x cubed is congruent to 0, 1, and negative 1 mod 9, as we saw in the Lewis equation. We have x to the 4 is congruent to 0, 1, 5, and 16 mod 20. And the last example that I'll give you is x to the power of 5 is congruent to negative 1, 0, and 1 mod 11. And this particular one can be generalized to Sophie Germain primes. I don't think it's known if there are infinitely many of them, but Sophie Germain primes are P such that 2P plus 1 is also prime. And so what happens then by Fermat's little theorem is that x to the power of 2p is congruent to 1 mod 2p plus 1. And we can do sort of difference of squares argument to show that x to the power of p is congruent to plus or minus 1 mod 2p plus 1. And that's if x is co-prime to 2p plus 1. And if it's not, then x to the power of p is congruent to 0. So the residues are 0, 1, and negative 1 mod 2p plus 1 for x to the power of p. The pth powers. So that is a generalization of this example. So yeah, there are heuristics that you can follow. You'll have to do some experimentation, but this is a technique that comes up quite often on contests and olympiads. Thanks for watching, and I'll see you next time.